Good morning, everyone. So we are in the third session of the season, transfer learning and its application. So far we had two presenters presented different application as well as problems in the domain of transfer learning. So today I will continue the series by talking about research published in AAAI 2017. The title is Distant Domain Transfer Learning. And interestingly, the problem that this paper addresses is the same problem as first paper that I presented. So let me remind you again what is that problem. So this is a framework of traditional transfer learning model, in which you have source domain data and you have a target domain data, and then the idea is you apply the knowledge that you learned from the previous task to improve or enhance the performance of the target task. And then one critical requirement for the success of the transfer learning algorithm is the source domain and the target domain, they have to be closely related. So that turns out to be the limitation of the traditional transfer learning model. It is a limitation in the sense that if you cannot find any direct relation between the source domains and the target domain, then possibly transfer learning probably will not work. Or even in the worst case, it will cause the negative transfers problem, in which will lead to the worst performance in the target task. So to illustrate, this paper showcase an example of image classification. So they have two transfer learning tasks here. The first task, the source data is photos of cat, and the target data is photo of tigers. And then the task is to detect whether a photo is a tiger or not. So you can see that using transfer learning, it can actually boost the performance of the target task as compared to a standard supervised learning algorithm. However, in the second transfer learning task, the source domain is photos of human face, and the target data is photos of airplane. So you can see the source domain and the target domain, they actually have very few commonality. So the performance of the transfer learning is actually worse compared to the supervised learning algorithm. So you can see in the first case, cat and tiger, they have probably they are animals from the same family, and then they have the same round face and hairy body. So they have pretty much similar features, which is not the same story with human face and airplane.
So what's the definition of difference? Because I still see some common in terms of the representation, that they are all images.
They are all images, so the features space are the same, but the distribution of the data is not the same. The features space are the same, but the distribution of the data is not the same.
So what is the difference to the reference model?
What's the difference between?
So last time we see some about text, right? And they don't contain the words in common, but they are all words in text form.
So the difference between two domains either can be they have different feature space, which is the case of text and images, or they can have the same feature space, but the data distribution are different. So it depends on whether you have same features or different distribution. So the solution, the idea for the solution to resolve the limitation of transfer learning is the same as the first paper, which is also use learning via sensitivity approach, and specifically they try to bridge the gap between the source domain and the target domain via some intermediate domain data.
So there was a previous problem.
The previous problem, and which is addressed in the first paper as well. And then this paper they propose a transfer learning algorithm. They name it selective learning algorithm. So come back to this case study. So now with this with the help of transfer learning via sensitivity, the selective learning algorithm can boost the performance of the second transfer learning task, and now you can see the better performance as compared to supervised learning.
Supervised learning, they use the target data only.
Yeah, so like they only use the label information of the target data, and then they build a classifier.
So what is the corresponding grade one for the first task?
The first one, they don't have the problem of unrelated domains between the source and the target domain. So they don't show the number for the first task, but the second task we can see the better performance of this new algorithm as compared to supervised learning.
Right. So I find it interesting that it could go even higher. Right?
It can go even higher, yes.
So where is that coming from? Okay.
Okay, so let's find out in this presentation. So I talk about the first. So in the first session, I presented this paper, Sensitive Transfer Learning, in which I have the same idea that you try to bridge the gap between the source domain and the target domain by some intermediate domain data. So the difference, according to this paper, according to the authors, is that the sensitive transfer learning model, they select the intermediate domain manually, and then they also use all the data they have at hand for the transfer learning task. Whereas in this paper, the intermediate domain selection process is done automatically, and then only helpful instances or helpful photos are selected, not all of them, because the idea is that not all the images or instances are useful for transfer learning. And the basic component for them to do that is the autoencoder, which is a type of feed-forward neural network. So let's talk a bit about this autoencoder. So you can see it's a feed-forward neural network, and then the input for this neural network is a feature vector, and then the idea is that this network will try to reconstruct this input vector X, and the hidden layer is received via an encoding function FE, and then you also have a decoding process which try to reconstruct the input from the hidden representation head here. So the objective function for autoencoder is they try to learn the pair of encoder and decoder function, so that they can minimize the reconstruction error. The error is actually the L2 distance between the original feature vector and then the reconstructed feature vector. And then the hidden representation here can be used for classification, or so it can be seen as a latent representation of the original feature vector. So then the problem that we having at hand right now can be formulated as follow. So you have a bunch of data in the source domain, which is label data, and then it is supposed to be sufficient to build a classifier in the source domain. So you can actually build an effective classifier for source data. And then you also have the target data, which is there's a couple of label data points, but it is too small to be an efficient classifier in the target domain. So that's why they cannot use supervised learning algorithm to be the classifier. And then you have a mixture of instances from many intermediate domains, which and they are unlabeled. So the idea of this problem is how to transfer the knowledge from the source domain to the target domain via this unlabeled intermediate domain data. And the assumption is that you have you can have same feature space, but the data distribution are not the same between the target domain and the source domain. So that's why. So first of all, because you don't have enough data. Because you don't have the similar distribution, so you cannot use traditional supervised learning algorithm to build the classifier from the source domain to the target domain. So, so the idea of transferring knowledge from the source domain to the target domain using autoencoder is as follows. So imagine that if one instance is useful for building a classifier in the target domain, then when you fetch the instances from the source domain and the target domain into this autoencoder, it will induce a small reconstruction error on all instances. Okay, let me say it again. If the one instance in the source domain is useful for the target domain, for the target task, then when you fetch this instance to the autoencoder, it will induce a small reconstruction error of that source domain instance. And thus it is the same when you fetch the instances from the target domain. So the autoencoder, right, will return you a reconstruction error whenever you fetch a new feature vector. And then, so the idea of this paper, they say that one instance is helpful for the target task. If that instance, if you can actually learn the pair of encoder and decoder function, which induce small reconstruction error for all instances from all domains.
They learned one autoencoder for all external automation.
Yeah. So let's say like all the source domain instances are useful for the target task. Then when you fetch those instances to the autoencoder, then you can actually find a pair of encoder and decoder that can return small loss for those data, both in the source domain and the target domain.
But do you use the autoencoder to train the target first?
No, they will fetch all the data from the source domain and the target domain.
Probably it's small compared to what?
It's more like so it will induce the reconstruction error, right? It is so you expect that it is as small as possible.
But that means when the models haven't done yet, so you don't know what is small. It's maybe sometimes get locked in this one is small.
Yeah, so the idea it should be as small as possible, right?
So without the source domain, when you just train only the target domain, it's still because all is small.
No, now the idea is that it should be. But when, for example, if you change only the target instance, right? It will return you a pair of encoder and decoder, and then you use that encoder and decoder to report the reconstruction error on the source instances. It might return a very big loss, right? So if you want to transfer the knowledge from the source instance to the target domain task, then you expect that the reconstruction error are small for own source or own domains.
So it's still in the at first we have to try on the type to make the autoencoder stable. And
No.
we apply put some instance from the source, and then we know that's whether or not the errors become smaller and smaller.
No, they use on the data, not only target data. They use all instances from all domains. So learn it simultaneously.
So this is just one pool.
That's one pool. Yeah.
Just one pool of all instances, and
Yeah.
you learn the same with all autoencoder.
Yeah. And then that autoencoder also returns small reconstruction error for all instances.
If the capacities of the model is very big, it's in both domain.
I'm sorry.
If the capacities of the autoencoder is big, it's just for target and source domain.
Yeah. However, we don't have enough label target label data in the target domain, so I don't think it could be sufficient or capable of work for both source and intermediate domain data.
What it means is the hidden nodes, if you put enough number of nodes,
Yes.
they can even split them. So then say, you work on this nodes, I work on this nodes, and I can represent both independently. They may not force them to be together.
They may not be awesome, but so the idea of learning on those instances via same autoencoder is to have the a common parameter so that the knowledge can be transferred from the source domain to the target domain.
Let's move on first.
Okay. However, as I mentioned earlier, not all instances from the source domain and the target from the source domain are useful to build a classifier for the target domain. So you need to have a selection scheme so that you can detect what are photos and what are instances that are useful to improve the performance of the target task. And the story is the same between the intermediate domain instance and the target domain instance. So then, given that you have a selection scheme to detect useful photos from the source and the intermediate domain, you need to learn the parameters, learn a pair of encoder and decoder to minimize the reconstruction error on those selected instances and on the target domain instances. So that's the general idea. So talking about the reconstruction error, it actually consists of three different smaller errors. The first one is a reconstruction error for the source data instances, and the second one is a reconstruction error for the selected intermediate instances, and the third one is a reconstruction error for the target instances. And this is a mathematics expression for the reconstruction error, in which you learn you need to learn the pair of encoder and decoder, and then you also need to learn a decision vector. So specifically the first one is the reconstruction error for the source instance, this one is for intermediate, this one is for the target, and the V vector here is a selection vector. It will take the value of 1 if that instant is selected. It will be 0 if it is not selected. So this is to control what are the useful instances you can use for transfer learning. And if you look at the expression for this regularization, then this actually encourages you that you should have as many useful instances as possible. However, the autoencoder is unsupervised model. So the output, the hidden representation head here, is probably not relevant to the label information, or is not fit with the classification task. So you learn, you just fetch the input vector, and then you will receive some hidden representation. But that hidden representation probably is not good for building the classification. So they want to have a better hidden representation by incorporating the label information into the network. So how? They actually make use of the label data. So for the label data, when you learn a hidden representation, you also need to learn a classifier that can fit as many labels that you have at hand as possible. And that is done by a classifier function fc here. So this process will induce another loss function which define over label data from the source domain and label data in the target domain and the unlabeled data in the intermediate domain. So this is a label data, so you can actually define a loss function between the two label and the probability of the predicted label. And this one, because the intermediate domain instances, they don't have label, so they use entropy function to say that I want to select the most likely instances that are helpful for the transferring process. So overall, this architecture will induce two different types of sub-loss. First one is a reconstruction error, and the second one is a classification error. And then this going to be the sum of these two loss function will be the overall objective function that you want to minimize. And then the constraint is that the selection variable should be either 0 or 1 for instances of photos from the source domain and intermediate domain, because you don't want to include all of those images from the source and the intermediate domain.
So which one have labels again? The source or the target?
The source and the target, yes.
So the classifier predicts which labels? The source labels or the target labels?
Both.
Both of them.
Yeah, they will share the same classifier function. I forgot to mention that they assume that the tasks in the source and the target domain are binary classifier. So they probably can pretty much can set the same architecture.
But even binary classifier, I mean, then there has to be a mapping, right? Because there's class 1 and class 2 here, class 1 and class 2 here. How do we know class 1 should 1, class 1 here, class 1 should 1, class 2 here?
So because the hidden representation are the same for a source data and target data, right? So then, if it is useful to have improving the performance of the target task, then you can actually have a common classifier to minimize the classification error in both source domain and target domain.
Let's move on first. Maybe back to the
Okay. So this algorithm is block coordinate descent, in which one at a time they fix one parameter and then they update the other parameters. So if they only selected useful instances from the source and the intermediate domain, they will update the parameters of the autoencoder. Or when you fix the parameters of the autoencoder, they will try to select a new set of useful instances to perform the transferring process. And there is an architecture that is shown in the paper. So the additional component here is a layer of CNN network. So they say that because the input layer of the autoencoder doesn't capture the spatial information of the image, so they have the option of putting convolutional neural network here to capture that spatial features of the image. So this one is optional. If you have the feature vectors at the beginning, then you don't need this one. But if you have the photos, the original photos, then you can fetch through this one first before you fetch the feature vector to the autoencoder. Sam, you seem to have a question, Prof. Okay, so having understood the framework, I will move to the experiment part. So the baseline here can be categorized into 3 different types. The first one is supervised learning, which you learn directly a classifier from the label data from the target domain. And there are 2 instances, which is SVM and convolutional neural network. The transfer learning baseline includes 5 different transfer learning algorithms, and especially one of them is transitive transfer learning, which was presented in the first session. And the third type of baseline is self-taught learning, in which you don't have the notion of source domain. You actually just pull all instances together and learn a universal feature representation via autoencoder, and then you build a classifier based on those universal feature representation.
So how is the information about the source domain useful? Because we just pull everything together, right?
Yeah, so they don't make use of that.
So how is that different from the SLA?
How is that different from
The proposed method?
the proposed method? They actually make use of the label information via a layer of classifier.
So we make use of the label information.
Yeah. So this one, when you have a label instance from the source domain, it can go through this layer, and then you try to learn parameters of the classifier that can fit as many of that label as possible.
Okay. So shouldn't they have a baseline that basically does the supervised learning just by pulling everything together and mapping the classes? So in this case, I will have, so I have the source and the target task, right?
Yes.
So the source means that we try to predict whether there is a target or not. No, human.
Yeah.
So human is 1, non-human is 0.
Yeah.
So then I will say airplane is 1, no airplane is 0. So then I have basically just combined the data set into a single data set. Then I can use a classifier.
No, I think the target task, the classification is not between what photo is airplane and what photo is a human face.
Yeah, so human face is 1,
Yeah.
no face is 0. So that's one task. So the other task is 1, airplane is 1, and then no airplane is 0.
Uh-huh.
So if we just combine them and just map airplane to face.
Could be, but yeah, they don't consider that baseline in the experiment.
I think let's move on to the experiment more details, and we will back here.
Okay. So the data sets that they use to synthesize the transferring tasks are 2 publicly available data sets. The first one is Cortex 256, which have more than 30,000 images from 256 categories. And then the way they synthesize the transferring task is they pick 6 categories: face, watch, airplane, horse, gorilla, and villas. And among these 6 categories, they pick one as a source domain positive image. Positive image will be one class in the source domain, and then the later one there will be a negative image, which is another class in the source domain and the target domain. So the task is classification, right? So you should have a positive side and negative side. So they pick one from one of these 6 categories to be the positive images for the source domain and the target domain. And then later they sample from another category to be negative images. and they guarantee that there is no overlapping images between the target negative images and source negative images. And all other images from the unselected categories will be pulled into intermediate domain instance, no label. And totally they have 30 pairs of domain transfer learning tasks. And similarly with the second one, with the second data set, which is animal with attributes data. However, this one they don't have the raw images, and what they have is SIFT features of more than 30,000 images from 50 categories. And the way they synthesize the transfer learning task is the same. So the performance, so overall, the proposed algorithm outperform on the baselines, both in the case of using additional CNN layer and the case of not using it. So the first comparison here, they actually have the CNN and they compare. So you can see that there are some transfer learning method which report worse performance as compared to supervised learning algorithm. For example, deep transfer learning as compared to CNN, it reports lower performance. In the case of using SIFT features vectors, then we also see SVM report significantly higher resolve as compared to deep transfer learning and even like sensitive transfer learning. The same story you can see with the animal with attributes data.
So this is the average of pairs.
This is the average of pair, yes. So this table has specific results that they extract for some example tasks. Pretty much you can predict that we have better performance of the proposed model. Okay, and the second experiment is pretty interesting. They try to understand how does the intermediate domain instance can help to transfer the knowledge from the source to the target task. So this is the images of human face in the source domain, and then they try with two different set of target domain. So the first one is photos of airplane, and the second one is a photo of watch. So you can see that moving from the source domain to the target domain, there will be some selected intermediate images, and this is appear in order. Like in the first iteration, these images will be selected. The second iteration, these images will be selected. So it's kind of hard to explain what is logic, what is the underlying logic of this transition of this order. But they say that you can see these are images of human face, and then this one is photos of Buddhas. So like they reflect some human features, human face features like round face and with hair. and then the next one was have some similar shape with the previous one. Like you see that they're both tall and narrow. Yeah, so they see that you can actually feel there's some similarity between those images. And they also report the number of the source images over time. So you can see that when they go when the model learn, then the number of source instances will decrease, which means that the knowledge now they transfer via these intermediate domain instances. No longer they rely on the source images. So talking about the order of the appearance of the intermediate domain, they also try to understand how useful this order is. So they compare the selected learning algorithms ordering with 3 different manual design order. First one is random. They basically just put all the category in random order when they change the autoencoder. And second one is category, which they borrow the ordering of the LSA model algorithm, and then they add additional intermediate data, and then they fetch this into the autoencoder. And the last one is a reverse one. Basically, they just reverse whatever they have in the second strategy. So the results show that the ordering induced by the proposed algorithm performs the best, and the runner-up is a category strategy, which makes sense because it borrowed the ordering from the proposed algorithm, and they added some noise, so it has lower performance as compared to LSA, but it is still the best as compared to 2 other ordering strategies. So in summary, the problem that this paper tried to address is the problem transfer link from the source to the target domains in which they are unrelated or quickly related. And the papers propose a selection learning algorithm which gradually select unlabeled data from the intermediate domain to bridge a gap between the data distribution. The experiments show pretty promising results. However, I still have a couple of questions about robustness of the model, like whether this one can handle the case in which the source domain and the target domain they don't have the same feature space, like in the case of text to image transfer learning, which is addressed by the transitive transfer learning paper. And the second question is whether this selection learning algorithm can resolve the problem of unrelated intermediate domain instances. So let's say you have a lot of instances in the intermediate domain, however none of them is useful or relevant to the target task. So whether the model can detect that problem by not using any instance in the intermediate domain or not. So then with that, I would like to end the presentation here. Thank you for listening.